So this is the video for section 3.1, and we are learning two new rules for taking derivatives. So right now, before we start this, just a reminder, the two rules that we have for derivative are the simple power, which would look like taking the derivative of x to the 1/2, and the general power, which would be more like the derivative of 3x squared minus 2x to the 1/2. So for simple power rule, our derivative is move the 1/2 down and drop the degree by 1. So we end up with 1/2 square root of x, because we get x to the negative 1/2. And with general power, we have to remember the chain rule. And that's going to come into play with what we're doing today too. So we would do the exact same thing. The exponent up here would come down in front. You do not change the function that the exponent's done on. You do subtract 1 from the exponent, just like you do in simple power. But then you also have to multiply on the derivative of the inner function, which would be 6x minus 2. So that's just a reminder of the two rules that we have now. But what we don't have is a rule to take the derivative of, let's say, 2x squared minus 5 cubed times x plus 6 to the 7th power. We haven't talked about how to do a derivative like that, other than multiplying it all out, which would take a long time, right? We'd have to multiply, cube this, take that to the 7th, multiply them together, and use the simple power rule. Because we don't have a rule for the product of two different functions to take its derivative. So short of multiplying it all out, we'd be stuck with a derivative there. We'd be okay if this was just a 7, and we have a rule for that. We have a rule for constant multiple times a function, but not a function times a function. And same thing with if I took these two functions and put them over top of each other. We don't have a rule for taking the derivative of that. Although it's tempting to think that it's 4x, so you take the derivative of the top and the bottom. It doesn't work that way. There's a more complicated rule for it. So we're not going to talk about why the rules that we have work. They have to do with our limit as h goes to infinity of the difference quotient, and that being the way that we get the derivative. But someone came up with these rules for a function times a function, and they did a limit on it, and the rule called the product rule came out of it. And the same thing with a quotient, a function over a function. They did this limit and found the quotient rule, and we're just going to use them. So here's the product rule. If you're trying to take the derivative, remember that's what this says. It's like a verb of a function times a function. The rule says leave the first function alone, multiply on the derivative of the second, plus leave the second alone times the derivative of the first. So shorthand, we could say fg prime plus gf prime. And we're just going to sort of verify that this works. This isn't a proof or anything, but it's just a verification. Because if we had two functions that we actually could easily multiply together, we could take the derivative by foiling first and then using the simple power versus using this new product rule. So if we FOILed out, we'd have 6x to the 4th plus 2x cubed minus 15x squared minus 5x. And our derivative with the simple power rule would be 24x cubed plus 6x squared minus 30x minus 5. the product rule says the derivative should be the first times the derivative of the second plus the second times the derivative of the first. And what I found over the course of teaching this, that some people, when they first learn it, are more comfortable making a little table of what those things are. So the first function is f. Its derivative is 6x squared minus 5. The second function is 3x plus 1. Its derivative is 3. And then we're going to do a little cross multiplication here and say the derivative should be 2x cubed minus 5x times 3 plus 3x plus 1 times 6x squared minus 5. So in this case, it definitely would be faster to FOIL and then take the derivative with the simple power rule, because here we're going to have to distribute and FOIL and add after we did the derivative. But for the most part, we're not going to really, if we have a choice, we'll go this way, but for the most part, we're not going to have a choice in this section. But let's just verify that we get to the same point. So we have 6x cubed minus 15x. And then here we have 18x cubed minus 15x plus 6x squared minus 5. And when we combine that all up, 24x cubed, yes. And 6x squared, yes. A negative 30x and a, minus 5. So we get the same thing either way we decide to do it. If we're looking at a problem like this second one here, we definitely do not have a choice, because this is to the fourth power, this is to the fifth power. Short of actually doing those to their own, each to their own power and then multiplying them together, the simple power rule is not going to be an option. So our first function and our second function. So now I know this is called f. If we want to be picky about it, I'll call it h. So I can call this first function f and this one g. But first and second functions. So the first function is x squared minus 1 to the fourth. And the second function is x squared plus 1 to the fifth. Our first derivative then would be 4x squared minus 1 cubed. And we can't forget the chain rule, times 2x. And our second derivative would be 5x squared plus 1 to the fourth times its derivative of the inner function, which is also 2x. Oops. So putting that all together, we're going to multiply this diagonal and add them together. And that's going to look like the derivative of our original function is going to be, I'm going to put the 2x and the 5 together to be 10x. And then I'll have x squared minus 1 to the fourth and x squared plus 1 to the fourth. So this diagonal multiplying the 5 and the 2x, and then I have a factor of x squared minus 1 and x squared plus 1. Plus, on this diagonal, we have a 4 and a 2x, which will be 8x. We have, I'm going to keep it in the same order, x squared minus 1 to the third and x squared plus 1 to the fifth. So this is multiplication, and I can put the factors in any order I want. But I put them in this order because the next step is going to be where we started this whole semester, factoring out the greatest common factor. This is the derivative, but if we're going to try to get critical values from it, we're going to need it to look different. So now I'm going to take a look at 10 and 8 and factor out a 2, x and factor out an x squared minus 1 and factor out the lower of the 2. So instead of the fourth degree, I'll pull out the third. And x squared plus 1, instead of the fifth degree, I'll pull out the fourth, the lower of the 2. And what's going to be left inside is I'm going to take this whole thing and divide it by what I pulled out, which is going to leave me with a 5 and an x squared minus 1. Because 4 minus 3 means there's one of those factors left. Plus 4, and here I'm going to be left with the x squared plus 1, because 5 minus 4 means one of those is left. And then my final step would be to just distribute inside the parentheses and combine. So I'll have a 5x squared and a 4x squared, which is 9x squared, and a negative 5 and a positive 4, which is negative 1. And if I wanted to, I could then factor 9x squared minus 1. Just depends how far I want to go with the factoring. So that is the product rule. It's going to take some practice. It's going to take the algebra skills that we did at the beginning of the semester. So if what I just did there is hard for you, you need to practice it, because that's what we should have gotten accomplished at the beginning of the semester for such a time as this. The quotient rule is a lot like the product rule, a little bit more complicated because the answer is also a quotient. And the way I say it in terms of a mantra for me is, if you take the derivative of a function over a function, you want to take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. And so if you look at this problem, it's very tempting, and believe me, I've had a lot of people do this. They want to say the derivative is 1/2, and it's not. You need to set up your table again, if that's helpful for you, and put your f as the numerator, your g as the denominator. The derivative of f would go here, so the derivative of x, and the derivative of 2x plus 3. We are going to do the multiplication again, but this time we've got to start on this diagonal, the g diagonal, because that's what our numerator begins with, g times f prime. So 2x plus 3, and then we're going to take f times g prime, which is 2x, all over g squared, 2x plus 3 squared. And then that's going to simplify down to 3 over 2x plus 3 squared. So that is our y prime, that is our derivative. So moving on to the back of the sheet, there's another example. What I'd suggest you do is, turn the video off for a second, pause it, try it, and then you can check your answer against what I've got here. So I got my 3x squared times x squared plus 1 to the 4th minus my 8x to the 4th times x squared plus 1 cubed. And now I'm ready to factor. I'm going to factor out an x squared and an x squared plus 1 to the 3rd power, because I'm comparing these two things and seeing the common factor. And this x squared plus 1 is to the, should be the 8th. Sorry, and square my denominator. So that's to the 8th right now. Denominator squared. And what I'll be left with here is a 3 and an x squared plus 1 minus an 8 and an x squared. So when I simplify that all down, I'll let x squared plus 1 to the 8th divide out x squared plus 1 to the 3rd. And I'll have my x squared, and then this is a 3x squared plus 3 minus an 8x squared. So I'll write that as 3 minus 5x squared. So could be negative 5x squared plus 3. So again, if that's not comfortable for you, just practice it until you get where you need to be. Derivative of f, derivative of g. Don't forget the chain rule if you need it. Multiply this diagonal first, and then this diagonal, and then make your subtraction, factor out your common factor, and divide. And don't forget to square the denominator like I did. All right, there's a couple other examples here. Combining rules can get a little tricky because there's 3 levels of function going on here. Well, let's break it down to just 2 levels of function. There's a division function and there's a square root function. And so you have to decide which you want to be the outermost function, the function that's done last. So if I plugged in a 1 right now for x, I'd square it and add 7 and I'd get 8. I'd add 1 and get 2. So I'd have 8 over 2, and I'd probably do that division, and then I would take the square root. So I'd have 8 over 2, which is 4, and then I'd take the square root. But another way to think about this function is each could have its own square root. You could give the square root to the numerator and to the denominator, and now if you plugged in a 1, you would get 8, and then you take its square root, and then you get 2 and take its square root, and then you do the division. So either way is going to get us to a derivative, but this one is the one that's actually more simple algebraically. It's much more simple to think about a function, just the division problem, and use the quotient rule. Otherwise, you would have to, it'd be very crazy. You would have an outer function of a 1/2 power, and you'd have to move the 1/2 down, change this to negative 1/2, not change this, but then multiply on the derivative, which would require the quotient rule. So you'd need the general power together with the quotient, which is more complicated. Although if you want to go for it, try that. So now I've got my first function and my second function. The first one is the numerator, and the second one is the denominator. So the derivative of the numerator is 1/2 x squared plus 7 to the negative 1/2 times 2x with the chain rule. The second one is 1/2 x plus 1 to the negative 1/2 times 1, because the derivative of x plus 1 is 1. So now I'm going to set up my derivative, which is going to be the denominator squared, which is just x plus 1. Then I'm going to start with my g and multiply on my f prime. So g is going to be x plus 1 to the 1/2, and this 1/2 and that 2 are going to multiply to 1. So I've got an x and an x squared plus 7 to the negative 1/2. I like to put my x in front. It's just a habit I have. So I would write it as x plus 1 to the 1/2, x squared plus 7 to the negative 1/2. Minus, now I'm multiplying f times g prime. So I have a 1/2. I'm going to keep the same order, x plus 1 to the negative 1/2, and x squared plus 7 to the positive 1/2. So I'm getting into here, sorry, should have left a little more room. So now it's time to simplify. So my simplification for this is my derivative, is going to be x plus 1 still in the denominator. I'm going to factor out an x plus 1 to the negative 1/2, which is the lower degree, and an x squared plus 7 to the negative 1/2, which is the lower degree. And then I'm going to factor out the 1/2. So that's going to leave this as simple as it can possibly be. So again, you might say, well, how do I factor out a 1/2? There's no 1/2 here. Remember that you can always put one there. It can be 2/2, which is just 1. So what I'll be left with here is the 2. I may not have left myself enough room. And the x. And since I factored out negative 1/2 factors of x plus 1, I'll have one of those left. Minus, on the other side, I factored out the 1/2. I factored out all the x plus 1s, but I'll have my x squared plus 7. Very important to put parentheses around that because I'm subtracting all of it. So just like the difference quotient, the quotient rule has a subtraction in it. You're going to have to be careful that you distribute it. So my final answer, I can pull this 2 down to the denominator with the 3-story building rule. I can pull the x plus 1 that has a negative exponent down there as well. So that'll be x plus 1 to the 3/2. I had a factor and I brought another half down. My x squared plus 7 to the 1/2 will stay up. And then I will have a 2x squared minus an x squared. And I'll have a 2x and a negative 7. And that is my final answer. Okay, so again, this algebra might take some work. You may be spending a little bit of time here trying to get a hold of it if you didn't at the beginning of the semester. All right, so looking at number 2, same thing I could do here. Instead of trying to have a root around a product and have to do the root and then the product inside, we're going to do a little rewrite and make it x plus 3 to the 7/3 times 2x minus 1 to the 5/3. So we're trying to get the outermost function to be either multiplication or division. That's our goal. And not a root as our outermost function. So now this is my f and this is my g. And I'm going to take the derivative by having my, I can do the, if it helps you on the side, you can do this as well. I'll do it here, but I don't want to make a big mess. So x plus 3 to the 7/3 and 2x minus 1 to the 5/3. So this is f, this is g. F prime is going to look like this. So I got 7/3, x plus 3 to the 4/3 times 1. G prime, 5/3, 2x minus 1 to the 2/3 times 2. The derivative of the inside. So those are my pieces. I'm going to take f times g prime. So 5/3 times 2, I'll call that 10/3. X plus 3 to the 7/3 times 2x minus 1 to the 2/3. Plus, now the other diagonal, 7/3. X plus 3 to the 4/3 times 2x minus 1 to the 5/3. So there's my derivative from the product rule. And now I'm going to factor out a 1/3 and x plus 3 to the lower of the 2 degrees, which is 4/3, and a 2x minus 1 to the lower of the degrees, which is 2/3. And I'll be left with 10 x plus 3 to the 3/3, which is 1, plus 7 And this time my x plus 3 factors are gone, but I have the 2x minus 1 to the 3/3, which is the first power. So my final answer is those factors, and then 10x and 14x is 24x, and 30 and negative 7 is 23. So I have all three factors, and if I need to set them equal to 0, it will be easy. The final part to this is we talked about minimizing marginal cost, but we're going to talk about minimizing average cost. Average cost is what you get when you take your cost for all of your products that you make and average it out per product. So if I'm making bracelets, how much does it cost me per bracelet? Not total, but average. So my average cost function, if I wanted its derivative, would require the quotient rule. I'd need to square the denominator, start with the denominator, which is my g, times my f prime, which would be c of x, minus c of x times 1. So my average cost function would look like x c prime x minus cx over x squared. And if I want us to minimize that, I need to set this equal to 0. That means I need the numerator to equal 0. That's the way you get a fraction to be 0. So I need x c prime of x minus c of x to equal 0. Which means to solve for x, I would move the c of x to the other side and divide by c prime of x. So the value of x that's going to minimize my average cost is the same value that I get if I put the cost function over the derivative of the cost function. And so the derivative of the cost function is MC, and the cost function itself, the derivative of the cost function is marginal cost, and the cost function itself is right here. So if we look at these two pictures over here, average cost is c of x over x. So if I flip-flop these diagonals, instead of solving for x, we know we have a property in math that if we have a fraction equal to a fraction, we can flip-flop on the diagonal. Marginal cost could go here, c of x over x could go here, but the name of that is average cost. So basically, we can minimize average cost if we make our marginal cost equal to our average cost. That's what this point is right here. So if we pick the point where average cost and marginal cost are equal, that will give us the x value that minimizes our average cost. And so this is something that I've done in general, so now we can remember it always. If you need to minimize average cost, set your average cost equal to your marginal cost and solve for x. And that is the end of the lesson. I hope that you are able to complete your stat lab based on this, and I will see you after break.